All right, today we're diving into a huge shift in how things get made. It's a powerful manufacturing method called cell production. And honestly, it's a pretty elegant solution to a very complex, very modern problem. So let's get right into it. So I want you to picture a factory. The classic image is that one long conveyor belt, just churning out thousands and thousands of identical products. But what happens when we want variety, when we want things customized? That single, rigid assembly line, well, it just can't keep up. So how do you build 1,000 different things efficiently, all under one roof? And that question right there, that gets us to the heart of what we're talking about today, the modern factory's dilemma. The whole manufacturing world has changed, and the old ways of doing things are really struggling to adapt. We have moved way past the age of one size fits all. We're now deep in an era of what's called high-mix, low-volume production. Just think about it for a second. Our phones, our cars, our computers, they all come in countless different versions, and new models come out so fast. This massive demand for variety is exactly what makes that traditional high-volume assembly line so inefficient today. So how do factories actually solve this puzzle? Well, they need a system that's nimble, adaptable, and still super efficient. And that system is called cell production. It's a complete rethink of what a factory floor even looks like. So what is it really? Okay, first, forget the long, moving conveyor belt. Instead, I want you to picture a small, self-contained little workstation. They call it a cell. And inside that cell, a single highly skilled worker, or maybe a small team, builds an entire product from start to finish. It's a huge shift from just doing one repetitive task to actually owning the whole process. Now this chart really lays out the difference perfectly. Line production is all about volume, right? The pace is set by the machine. And the worker, they're just doing one little thing over and over. But in cell production, the whole focus flips to variety. The worker sets the pace, and their role just explodes. They have to be a multi-skilled expert, not just another cog in a giant machine. This shows you that jump from mass production to mass customization. And this isn't just some theory. It's being used to build the complex, high-tech stuff we use every single day. Think about the kind of precision you need for a digital camera or a piece of medical equipment, or all the different ways you can configure a PC or a server. These are the perfect examples of high-mix, low-volume products, where a system like cell production just absolutely shines. Okay, so we've got the concept down, but what does it actually look like on the factory floor? Because the physical layout of the cell, that's absolutely critical for making it all work. Let's take a look at the most common designs. First up, we have what's pretty much the gold standard, the U-shape. The worker stands right inside the U, so everything they need is literally within arm's reach. They can pivot and turn, but they barely have to walk at all. This cuts out so much wasted motion, which makes it incredibly efficient, even if it does take up a little more floor space. Next, you've got the L shape, which is a fantastic compromise. It's way more efficient than just a straight line, but it's also more space-conscious than a U shape. It's a really practical, real-world setup that you'll see tucked into corners or built around columns on the factory floor. And finally, we have the simplest layout of all, the I shape, or just a straight line. Its biggest advantage is flexibility. It's super compact and really easy to reconfigure or move around. The trade-off, of course, is that the worker has to move all the way from one end to the other, which makes it the least efficient when it comes to movement. So we've designed the physical space, but who's actually doing the work inside it? Because the human element is every bit as critical as the layout itself. You've really got two main approaches here. The one-person system relies on a single multi-skilled expert who does the whole thing. This creates this incredible sense of ownership and personal responsibility for quality. Then, on the other hand, you have the multi-person system, which splits the work between a few people within that same cell. This is awesome for training new employees, and it gives you a lot more flexibility in staffing since you don't need every single person to be a master of every single task. So cell production seems amazing, right? It's flexible, it's efficient, it empowers workers. But, and this is a big but, here's the twist. This fantastic new system brings with it its own unique and incredibly complex set of problems. This is what I like to call the flexibility paradox. By creating a system that can handle this huge amount of variety, you also create a scheduling and logistics puzzle that is just mind-bogglingly difficult to solve. The freedom to build anything at any time, well, it definitely comes at a cost. Challenge number 1, skill management. You have all these multi-skilled workers, so you have to know exactly who can build what and how fast they can do it. If you assign a really complex server build to a trainee, or even a veteran who just happens to be slower at that one specific model, you can completely destroy the production plan for the entire day. It's like a human resources puzzle on hyperdrive. Then, you've got the absolute nightmare of parts supply. Imagine hundreds of these little cells, and each one needs a different set of parts at a different time, down to the minute. If the parts get there too early, they just clog up the tiny workspace. But if they're even a minute too late, your expert worker is just standing there, doing nothing, and a production line worth thousands of dollars an hour just grinds to a halt. And the third major challenge is load variation. One product might take 30 minutes to build. The next one might take 3 hours. So what happens when you get a sudden rush of orders for that 3-hour product? A dozen cells get totally overloaded while others are sitting there empty. It's not about keeping one line moving anymore. It's about balancing the workload across the entire factory, which is this constant dynamic juggling act. And finally, the one that ties it all together: constant change. A VIP customer has an urgent order. A supplier delays a critical part. An engineer changes a product's design. In this kind of environment, these aren't exceptions. They are the norm. And every single change sends a ripple effect through the whole system, forcing you to resolve the skill puzzle, the parts puzzle, and the load puzzle all over again in real time. Doing that by hand, it's basically impossible. So this is the crucial point we're left with. Cell production brilliantly solves the physical problem of building a high mix of products. But in doing so, it creates this massive information problem. It proves that the modern factory's biggest challenge isn't just about clever layouts or skilled workers. The real frontier is the brain that has to direct it all. And this is exactly why the most advanced factories now rely on really sophisticated scheduling software to manage all this complexity, to act as the digital conductor for this symphony of infinite variations. The challenge isn't just how to build, it's how to orchestrate,